So I'll talk to you about some work we've been doing to try to help visualize the output of complex model in a landscape context. So I'll start by giving you a bit rationale for this work. The major problem that a lot of modelers encounter is that as we gain a better understanding of complex systems, we have a huge computing power in developing models, and tons of models. Models about climate change, about population dynamic modeling, financial models. And those models tend to be dynamic, so we tend to have multiple variables that will be in multiple states through time. And in the spatial sciences area, you have spatial dynamic models. So you have a lot of variables, you have a lot of states, and have a lot of cells. So you end up with a lot of data, and usually looks like something like this. It's not really very friendly for the average user. And they tend to be actually very difficult to interpret and even analyze. When I look at some of my models, it's very difficult to understand what's happening. They tend to be very difficult to display with standard procedures. I mean, graphs are really nice if you only have one variable through time for one location, but if you start having thousands of graphs become very difficult. Maps are good for one variable through space, but if you start adding multiple variables or multiple time steps, it becomes very difficult to understand what's happening. And it's even more difficult if you want to communicate with people that actually don't really understand graphs that much. If you talk to policymakers or people on the ground, they don't really want to see graphs. They just want to see what does it mean for me, what's happening in my area. So my objective was to develop an approach to help better communicate the outputs of spatial dynamic models. So I focus on space and time for multiple variables. And try to develop 3 visualization approaches, and I try to illustrate them through one common case study so we can see the difference potential. The first one was to use animation using GIS, so standard GIS software, how we can make temporal animation. The second one used to the use of digital block technology, in that case mainly how we can use colors to display those data. And the third one was making use of 3D realistic representation of data. So my example model is a locus spread model. It's a conceptual model, so there's no real data into it. So when you look at the outputs, just don't. They're there. What's modeled really doesn't matter. What it's using is a cellular meta structure. So I model some population of insects within certain cells. So space is divided as square cells, and my population model is run within each of those cells. The insect model is relatively simple. I mean, 4 stages. 2 of them are immobile. They don't move at all. One is they're hoppers, so they can move from one cell at a time. And the other ones are the adults, and they have the capacity to fly. Their population is limited by how much grass is available, so as time goes by, they chew the grass and there's less grass. And in the end, when there's no grass at all, they just end up eating each other, so that's how I limit my insect population. As I said, they have the capacity to move, and there's 2 factors that impact them. First one is the presence of wind. If there's wind and they're flying, well, they go wherever the wind blows them. Otherwise, they look around at whatever place looks most suitable. If there's more grass, then they just go there. So just to give you a bit of context of what the model output will show you. Then the model was developed in Stella, and I used a spatial modeling environment to populate my model and replicate it in each cell of my grid data. And it gives also the capacity to exchange information between cells, so I can know how many adults move from one cell to the other, etc. The land use data, the data set that I used was a 30 by 30 meter grid. And I used a couple of land use maps, and I outputted 4 data from my models. My models was run an array time step, so I have 3,000 time steps. And for each variable, I have 12,000 grids, and each grid has about 6,000 points. So you have a lot of points, a lot of information. It's almost 1 billion data of information. So then I have to try to understand how I can help visualize and communicate the output of these models. That's the study site I run my model on. It's somewhere in Victoria. It's a relatively small area. This is my wind map, so you can see it's really conceptual, it's just made up. And the arrow tells you in which direction the wind blows through. And here is where I start doing my insect population. And then what I did is create this GIS automation in which through time we try to observe what's happening with this insect population. You can see here, the color tells you how many insects we have. If it's red, you have a lot of them. If it's blue, few of them. And you can get an understanding of what's happening with the dynamic. Initially you blue, and then we increase to red as the population chews the grass and increase in population. The method I use is relatively simple. It's all based on scripts because I have a lot of output, so I cannot do it manually, and it's just all batch. There's 2 main interfaces. One is Python to do the data transfer. The other one uses VBA mainly to illustrate, to create symbology and apply it, and create the overlay with aerial images. And I end up with an image sequence, and then using software like QuickTime, you can just add them into one API. This type of approach has major advantages above current maps. Well, the first one is that you have animations, you have a temporal view there, so spatial and temporal animation. You can have some level of contextualization, as I did, if you overlay about aerial imagery or over GIS data if you have them. But you have a limitation. You can display usually only one variable at a time, because if you have multiple variables there, it's going to be very messy. You don't really have any control on the frame number, so I can stop the animation, but I cannot know exactly, oh, this is this time step, and this is what's happening for this specific time step. There's no real possibility of query data, it's just a moving animation. And you have no real possibility to change your mind and want to have a look at it from a different perspective. So if I want to rotate the map or go down on the ground, this type of interface doesn't allow you. So that's why we try to develop, that's one way to alleviate one of the problems of having multiple variables is using some image processing software. Here you can see the adult population, that's my Hopper's population. You can see the cracks being shoot and disappearing, and that's the larvae. The advantage that it looks a bit better, the problem is that it's not really easy to automate because you're working with a different software. So that has some limitations. And so the next approach we developed was try to make use of digital globe interface. That's pretty much the final output here. You can see we have an animation. The animation is exactly what I displayed before, except now you're in the landscapes context. So you have, you can see there were some mountains a little bit around, and you have some information that help you contextualize what's on the ground, and you don't need to have it, it's already provided by Google. And you can just follow the population and go through time and just change your mind and say, oh, what does it look like from this or that point of view? The advantage of digital globe is that we can associate also for each point, each location, some clickable link and have a look at what's happening on the ground. So here, we have also the capacity to control the time frame with this slider bar. So here I'm looking at a specific time step. And normally you can associate for each cell a clickable point, but my cell being 30 meter, it was just too small, so I resampled it to a cell of 300 meter. And for each point, I can associate information, for example, here, of my grass population. Looking at the model outputs, I can produce a graph for this location, what's happening for my different time step. And you can associate those graphs through every life stages, for example. You see the one with baby locust, but here that's the population of adults variation. So you have a way to query data a little bit more than you would normally. The method is pretty much similar. You use a set Python script and VBA, and for the to associate the graph is just only in Python, that's much easier. The advantages of this interface are pretty much all the advantages that you had in this GIS animation can be translated over to Google. You have a control of the time frame through this slider bar. It's much easier to get data contextualization because, well, the digital globe already provides you with the digital elevation model and the aerial imagery. You could also drape whatever imagery you like. You have a freedom of movement, so you can look at the data set from any angle or any place. And you have the capacity to create data through this hyperlink, but you have to kind of pre-process everything, so there's no real live link read at this stage. The other limitation is, again, you have a few variables that can be displayed in the animation itself, so you would have to turn on and off different animation if you wanted to see different variables. All the graphs are pre-processed, and it's quite difficult still to see have an indication of what's happening really on the ground. If I ask a farmer and I tell him, look, it's getting red in 2050, or it's getting red next week, well, he will tell me, what does it mean? What does it mean for me? So our third approach was to try to use 3D realistic visualizations that kind of give you an indication in the real landscape, well, this is what it looks like, this is what it means. The method that we use in that case is using one software that was Visual Nature Studio that you feed it GIS layers, and among those GIS layers you have your model output being ASCII grids or any types of data that will just batch import in the process. Then for each type of location, you can associate what they call ecosystems, or that's your variables, and you can control a lot of those parameters in those variables. Or you can use also 3D objects. And in the end, you end up either with a still image or a time series. The value of this tool is that this time you really have an observer perspective, and you have some accurate topography and landscape context. And you can, it's not just a pretty picture. Here I see it as a 3D with a depth representation of data or variables. So if you're doing a crop modeling, for example, I can control the size of my crop, the live stage.